Welcome to Escape Room Tech Bootcamp. If you know absolutely nothing about escape room tech, but you want to become a master of it, then this video series is for you. But I'm warning you, you're going to learn some things. So come on, let's get started. Hey everybody, welcome back to the Puzzle Creative YouTube channel for escape room owners. We're going to kick off a video series called Escape Room Tech Bootcamp. And if you know nothing about escape room tech, but you want to learn more, you are in the right place. So here's a quick overview of some of the things we're going to cover in this series. We're going to talk today about tools and terminology. And then in the next video, we're going to get into some projects. Project 1 is going to be a basic door maglock, classic escape room, with a keypad. Project 2 will be an object placement puzzle that includes use of either magnet switches or an RFID chip. Project 3 will be an object placement puzzle again, but this time with yes and no logic. You'll learn more when we get there. Project 4 will be a sequence puzzle where you have to press things in a certain order. Project 5 is going to be a series of tasks that have confirmation lights that tell you you're done with each one. In Project 6, we're going to get into metal and touch sensors. And then in Project 7, we're going to switch over to media players where you can learn how to trigger either audio or video files. Project 8, we're going to create delays using timer relays. Sometimes the thing that you trigger doesn't need to happen immediately, but later on. Project 9, we're going to work on reversing polarity so that you can control a motor or a linear actuator forwards and backwards. And we're going to be building all this tech from scratch, so no use of pre-made controllers here. So let's get started right here at the very beginning with tools and terminology. So right off the start, we need to talk about power supplies. How you're going to get electricity to all these devices we're going to be dealing with. So here in my hands I have a basic 12 volt power supply that looks something like this. Has a brick here in the middle, cord that plugs into the wall on one end, cord that plugs into a device on the other end. Now, what you need to know about this is that there are two types of power. There is AC power, which stands for alternating current. And that's what you're going to get from a building when you plug it into the wall into a normal socket like this. But then this little device here, it transforms it from AC power over to DC power or direct current on this side. And that's good because direct current is almost always what we're going to be using in our escape room props. Now, direct current has two different poles or positive and negative sides of the wires that you have to connect in order to get something to work. Think about a battery, like a AA battery. On one end of a AA battery, it's labeled with a plus sign, and the other end of the battery is labeled with a negative sign. That's because batteries also operate as direct current, and they have a positive and negative terminal, or positive and negative poles. Similarly, here on the output side of my power supply, I have two wires that run inside this barrel connector, and one of them you have to get to by plugging in the device. A pin will go inside the barrel, so there's metal inside the barrel, and that will give us either positive or negative side of power. And then on the outside of the barrel, we have the other side of power. So in order to connect a device and have it power flow, you have to be connected to both positive and negative. Where on the other side, alternating current works a little bit differently. You sort of have, like, let's call it a hot wire and then a ground. So not quite positive and negative, it just works a little bit different. Now, this power supply does have the brick in the middle, but your power supply that you purchase might look a little different. It might have the transformer like this connected directly to the prongs that plug in the wall, and that's perfectly fine. One interesting thing to do to look at is on your power supply. If you take a look at the label on your power supply, you'll have something that reads input and something that reads output. Now on mine here it says input AC, that's alternating current again, 100 to 240 V. V stands for volts. We'll get into that in a minute. The output here says 12 V or 12 volts. Now I know that the output is DC because right here at the top it says AC/DC adapter. So this is transforming AC power to DC. And 12 volt output is good, that's what we're looking for. The types of voltage that we're going to be dealing with in the escape room world are almost always considered low voltage. And this is anything that's below 50 volts. Now your building power that is AC power, that is also high voltage, and it's 120 volts typically. But anything that's low voltage, 50 volts and below, generally is not quite as dangerous to just touch with your bare fingers. You still have to have caution, but low voltage power is easier to deal with. So most common low voltage systems are going to use one of these denominations. It's either going to be 3.3 volts, 5 volts, 12, 24, or 48 volts. And the most common that we're going to see in the escape room world is going to be 12 volts. But also, almost all of the do-it-yourself microcontrollers like Arduino and Raspberry Pi, they're going to interface as 5-volt devices. So those are the two that you're going to need to get used to seeing. And you might also want to pick up a power supply from Amazon if you don't have one already. A 12-volt power supply would be a good place to start. And in just a minute, we'll talk about exactly what to look for when you're buying your first power supply. But before we jump into that, I want to jump to the board for a minute and give you a quick analogy to help you understand exactly what all these terms about power and power supplies mean. There are three main terms that we need to get comfortable with: volts, amps, and watts. So let's jump to the board and I'll show you how they all relate to each other. So let's take a look at a quick analogy that uses water flowing through a pipe to help us understand the different terms of electricity: volts, amps, and watts. So imagine for a moment that we have a pipe, and you can see the inside of the pipe here, the cross-section area of the pipe, and you have water flowing through a pipe like this. The rate that the water is flowing through the pipe, or the speed that it's going through the pipe, let's call that velocity. And the opening, the size of the opening of the pipe here, let's call that the area. Now, if you imagine for a moment that the area of this pipe is very small, but the rate of speed of the water flowing through it is very fast, you might think of something like a pressure washer, or even like a water jet cutter that can cut through metal. These things are very, very powerful and even potentially dangerous because the water's flowing so fast. But ironically, if you were to spray those into a large reservoir, like a huge bucket or a 55-gallon drum, there's not going to be a lot of water that accumulates because the total amount of water coming through a pressure washer, let's say, is not very much. On the other end of the spectrum though, imagine you have a large drainage pipe, like in a ditch or a sewage system that's multiple feet wide on the cross-section area, but the rate of speed is slower. If you imagine that dumping out, you could have the same or even more amount of water even though the rate of speed is lower. Now, the way that the electrical terms apply to this is something like this. I like to think of volts as similar to velocity. Volts would be similar because it sort of measures the speed at which electricity flows across a wire, the rate of speed that it's being forced through to your device, okay? And then amps is what you think about when you think of area or cross-section area of the pipe, and here's why. Volts, primarily what we're concerned with here is compatibility. What I mean by that is you need to make sure that the power supply you're buying matches the number of volts that your device needs. If they disagree, then you're going to end up either providing your device with too few volts or too many volts. If you have too few volts, then your device may not turn on at all, or if it's a light bulb, it may be too dim. And if you give it too many volts, more than likely you're going to cause damage to the device, like burn out the light bulb or the motor. And so if the primary terminology to think about with volts is compatibility, then the primary term we need to think about with amps is going to be capacity. What I mean by this is what is the total amount of power that is available for me to draw on at this rate of speed? So if you imagine that this pipe is really, really wide, and we want to hook up a few different water hoses to it, the supply lines to maybe water our yard or something like that, then if we have a large enough pipe here, there will be plenty of water to flow through all of the different water hoses with no problem at all, because the total amount of water is plenty and it's flowing at a good enough rate of speed that it's going to provide us pressure in those different water hoses. So for instance, in electrical terms, let's say that our velocity here, or our volts, is 12 volts, and the total size area of our pipe that's being provided by our power supply is 5 amps. And we need to hook up, let's say, 4 different light bulbs that each require 1 amp each. And we'll get into that calculation in a minute. But if each light bulb we know needs 1 amp to run, then we could have a light bulb here running on 1 amp, one here, and one here. And we are now at a total of 4 amps of power used on a 5 amp power supply, and we're good. And typically you don't want to go all the way up to the number of amps that are provided by the power supply. Typically you want to stay at about 75 to 80% or lower of the output of the power supply, just to make sure that you don't overload it. Now the last term that we need to put on here is watts. And watts is similar to water in this analogy because it represents the total amount of power that flows through. And that's what you need to think about watts as, is total power. Now how do these three terms relate to each other? Volts, amps, and watts. Well, let's take a look. So the relationship between volts, amps, and watts looks something like this. It's V times A equals W. Volts times amps equals watts. So this is really handy because if you're shopping for a light bulb for your escape room on Amazon and you know for sure that you need a 12-volt light bulb because you're going to stick with low voltage for this application and the power supply that you have is 12 volts, so compatibility is going to match. So we know that we're going to have a 12-volt light bulb here, but we need to figure out how many amps it needs, what size power supply in terms of amps we need to provide for it. Well, on the website on Amazon, in the description, they just tell us the number of watts of power consumption. Well, sometimes this is really inconvenient, but if you know the formula, then you could figure out from watts exactly how many amps it actually is that you need in your power supply. So for instance, let's say that they quote it as 6 watts. Well, then that means that this has to be half an amp, or 0.5 amps. So 12 volts times half an amp equals 6 watts. So that tells us that this is not very much power consumption, and we could put many of these light bulbs on one power supply that, let's say, is 5 amps or 10 amps. So one really important thing we need to talk about at this point is amperage safety. Amps flowing across a conductor like a wire can create heat. If you run too many amps through a wire that's too small, it will get hot. So how do we protect against this? By the way, this is called overcurrent, when there are too many amps that flow across a wire that's too small. Here are a few different strategies for how we can protect against overcurrent. Number 1, limit the number of amps provided by your power supply to 10 amps or less until you really know what you're doing. And even then, I would recommend that you never go above 25 amps for power supply. Why is that? Well, because whatever the max number of amps that your power supply can provide, that's the number of amps that will flow over a wire if it happens to short circuit. And a short or short circuit is where positive and negative wires from the power supply touch together without first passing through some kind of device. So that brings me to the second tip for protecting against overcurrent. Get a power supply that has built-in overcurrent protection. So for instance, if I were to take this power supply here and I were to cut off this barrel connector, which we'll do in a minute, and we often do, and just get to the bare wires under here so that I can connect them in a different way other than this barrel connector. And while I'm doing that, I have it plugged in for whatever reason, bad idea, but if I have it plugged in and the two wires on this output side happen to touch each other, it will create a little spark. But because this particular power supply has built-in overcurrent protection, that means it's going to detect that there's a short circuit situation and shut itself off. And this light that's on the front of the power supply would go from green to off. And it would stay that way until I took the two wires apart, and then the power supply would turn back on. So be sure to buy a power supply that has built-in overcurrent protection. The third strategy for dealing with overcurrent situations is to use fuses, especially when you're connecting devices and power supplies that were not specifically made for each other. Now, fuses are measured in amps. And by the way, a fuse is a little device that is like a tiny wire inside usually a plastic or a glass enclosure that if it gets too many amps that flow over it, it gets hot on purpose, but it's designed to break so that it will break the circuit and no longer allow current to flow through. So the number that's printed on a fuse is the number of amps that the fuse is rated to conduct on a regular basis. And if you exceed that number, then the fuse will blow and it's going to disconnect the circuit, and that's its safety feature. Now, the different types of fuses that are out there would be like glass fuses that look something like this. You can find these a lot of times in the multi-channel CCTV or closed-circuit TV power supply boxes, or maybe a blade fuse that looks something like this. Blade fuses I like to use because they're really easy to put in and out, and they're readily available, they're easy to purchase. And then there's another type of fuse called a PPTC fuse, or polymeric positive temperature coefficient. Now if you really want to sound smart around your friends, just say something like, oh yeah, I gotta see how many polymeric positive temperature coefficient fuses I need for my latest project, and they're gonna think you're just absolutely incredible. But really all that this means is a PPTC fuse acts more like a breaker than it does a fuse, meaning that a breaker in a house or a building, typically when you have an overcurrent situation, it just flips off instead of completely blowing out. A fuse is one typically that when it blows, you have to throw it away because it's done and you have to put a new one in. But a PPTC fuse, all it does is it will shut off the flow of electricity as it detects too much heat. And then as soon as the overcurrent situation is resolved and the heat of the fuse goes back down, it allows current to flow through again. So these are really nice because they actually don't blow out, and if you have a short circuit situation, you don't have to go find the fuse and replace it. So those are really nice to use sometimes. By the way, while we're talking about how to connect fuses, there are a couple of different ways to put a fuse into your wiring circuit. And one way you could do this is with an inline fuse connector. Let's say you're using a blade fuse and you just need one fuse hooked between your power supply and your device. A decently good way to do this would be with something like this, which is an inline fuse connector. And there's just one blade fuse that goes into that little harness that you can connect between your power supply and device. But if you're in a situation where you need one power supply to power lots of different devices on different wires, I would recommend going with a multi-setup that's more like terminal blocks that have indicator lights on them so that it's easier to tell when a fuse is out or not. Something like this maybe. We'll include links to all these products in the description below. Now the next strategy for guarding against overcurrent situations or amps flowing over a wire making it hot would be to use the right size wire gauge. Wire gauge describes how large the cross-section area of a wire is or how thick it is. Now it's counterintuitive, but just remember that a smaller number for wire gauge means a thicker wire. For example, a 24 gauge wire might look very small, but a 14 gauge wire is a little bit bigger, and then 10 gauge is even bigger than that. To find the right wire gauge for your application, you can look online by just Googling wire gauge calculator. There are a few different factors to take into consideration when calculating wire gauge size. The first is how many amps the device is going to be using. The second is how many amps that the fuse on that particular line is going to allow to flow through. And then the third one is how long the wire needs to be. You need thicker wire as the number of amps goes up or as the length of the wire goes up. Unless you know what you're doing, I recommend that you do not use wire that's any smaller than 18 gauge if it's going to be connected to a power supply. And if you're using it on a device that pulls a lot of amps like a motor or high-powered lights, be sure to use even thicker wire than that. Okay, let's say you're ready to start shopping for your first power supply. You have a few different options on style of power supply that you purchase. Once you determine the number of volts that you need so that it is compatible with your devices, let's say that it's 12 volts in our case, then you're going to be looking somewhere like maybe Amazon for 12 volt power supplies. You might see some that look like the one we looked at earlier that have a brick in the middle like this, or one that has the transformer that's connected directly to the plug. But you also might see some that are a little bit larger, that are in a metal box. This is the CCTV box that I mentioned earlier. Any of these would be perfectly fine. It just depends on exactly how many devices you're going to be using and what exact application you're going to be using it in. If this is your first time buying a power supply and you're just using it to test a few different things, I recommend going with something that looks a little bit like this. Now, I would also recommend for your first power supply to go with a 12 volt power supply and probably stick with about 5 amps. That'll be a good one to just get started and to try a few things on your workbench. Okay, so the next device we're going to talk about is a multimeter. Now, a multimeter is going to look something like this. And this guy does multiple things, hence the name multimeter. The first thing that we use this for all the time is going to be to read voltage, to measure voltage, and also to measure polarity. What do I mean by that? Okay, let's get into it. So on a multimeter, you're going to have a dial probably that looks something like this. All of them are a little bit different, but the labels are typically about the same. And there's one on mine that has a V. That V stands for voltage. So I'm going to set the multimeter to V to measure voltage. Then there are two different types of power. Remember, there's alternating current and direct current. Well, In order to use these probes to measure my type of power that I'm using is direct current, I need to make sure that this device is set for direct current. Now on here, there's a small symbol next to the V that has dashed lines. The dashed lines are direct current, and the wavy line is alternating current. And so I'm gonna make sure that I am set on direct current. There we go, and I can see the little dashed lines now in the window display screen of my multimeter. So now what I could do is I could hook up these two probes that are plugged into positive V on here and into COM or common. With these two probes, I can now touch onto bare wires or to the metal parts of the barrel plug of my power supply, and I can see what reading it is. So let's check it out. So I have my multimeter set correctly, and I have my power supply plugged in, and here's the output side of the power supply. We're gonna take these probes, I'm gonna place one on the bare metal part on the outside of this barrel, and then I'll place the other one inside the barrel so I can get contact to the metal that's inside there. And then I get a reading that says negative 12.25 volts. So this is reading at about 12 volts. The rounding error there is fine. Power supplies are gonna be a little bit above or below 12 volts typically. And the negative sign is interesting. So that's where we get into measuring polarity. If I'm not sure which side of the barrel is providing which side of power, positive or negative, I can figure that out using the multimeter. So here I have a red probe and I have a black probe. The red probe is plugged into the port on my multimeter that says plus V. So that's going to be the positive side of power. So whichever side of power on my power supply I touch this to, this is going to read it as positive, which must mean if I'm getting negative 12 volts on here, then I have it backwards because this power supply should be giving me 12 volts. So let's reverse. Instead of having the black inside the barrel, I'm going to connect it to the outside of the barrel, then put this one inside. And now I'm getting a reading of 12.25 or 26 volts with no negative sign in front of it. So that tells me that the prong that's inside of the barrel is my positive side of power, and this metal jack on the outside of the barrel is my negative side of power. Now the next thing that we can do with the multimeter is to measure the number of amps that are actually being consumed by a device. The way you would do this is after you connect a circuit, power supply to, let's say, a light bulb again, you could disconnect one of the wires going to the light bulb and then put this in between it to bridge the gap between the power supply and the light bulb and let power flow through the multimeter, and it will give you a readout that tells you how many amps the light bulb is pulling from the power supply. So in order to do that, we're going to set the dial to, there's something that says MA, and then something that has a little symbol and then an A. Either one of the capital A's is going to be amps. So there's also one that says 10A. That's the one, I'm actually going to go to 10A for 10 amps. And that just means, is the multimeter going to be capable of reading something that goes up to, let's say, 10 amps, or is it going to be really, really small amount of power? The MA stands for milliamps. I'm going to go with 10A for what we're measuring. I'm also going to make sure that I'm set to the right type of power. We're not in alternating current, we're in direct current. So I'll press this button so I get the dashed line up here in my window. And now I'm ready to read amps once I hook up to a device. So let's take a look at how we can measure amps on a device. Right down here I have a motor that's currently spinning, and it's hooked up to my 12 volt power supply. And in order to use the multimeter to measure amps and figure out how much power this guy's pulling, I'm just going to disconnect one side of the wire here from the power supply. So I'll just pick this one. Motor's going to stop because we broke the circuit. And then I'm going to take one side of this, put it in the clip here, connect it to the power supply, and then I'm going to now reconnect the circuit. It's now going to flow through the multimeter and out of this and into the motor. And it's back up and running again. And I'm seeing here readout on my multimeter is about 1.2 amps. So that means that this motor, with no resistance on the motor, like if there was some load that it was trying to carry or pull or something that was trying to move, it probably would pull more than that. But unrestricted, the motor running is running about 1.2 amps. And the power supply that I have down here is a 5 amp power supply. So this would be perfectly fine to run on this power supply. Now the third thing that we use the multimeter for all the time is to test continuity. And what I mean by that is to tell if a wire or something else metal is actually allowing signal or power to flow through it, or if there's a break somewhere in it. So to test this, we'll flip our multimeter over to this little symbol that looks like a Wi-Fi symbol on ours. And we get this OL that comes on our screen. And with ours, what happens when you touch the two probes together in continuity mode is it's going to make a beeping sound. Okay, so what that means is we have now closed the circuit and it's allowing signal to pass through. But we can also bridge this connection between the two probes with something else, but only if it's a conductor. Like this plastic remote, not going to work. It's not conducting electricity. But the metal on my wire strippers here is going to allow it to flow through, so we get a beeping sound when we connect using that. Now let's test on a wire here. So if we have a wire and we're going to try to see if this wire is actually going to allow current or power to flow through, then we would connect to one side with one probe like this, and then we would connect to the other side like this. It does, but it's intermittent like this, which means I think we have a short in this one. See, it's actually not doing it. Let's take another wire and try this one. So again, we'll connect one side to the bare wire that I've stripped off here, and the other one here. So this wire is good. So the next tool we want to take a look at are wire strippers. Wire strippers are essential for stripping wires. And you're going to need a set of these if you're doing any amount of work on escape room electronics. So I recommend you go ahead and buy a pair. Now, the ones that I have here are from Klein Tools. It's a good set. Got them at Home Depot. These run from size 10 gauge wire all the way up to 28 gauge wire. So you can see it has these tiny little holes when they're closed, and that allows you to strip off the outside of the jacket or the insulation of a wire, and to not harm the actual metal part of the wire on the inside. So for instance, I know that this is size 16 gauge wire. So on here, I can look at the label that says 16 and I can find that hole and I can place this wire in there. And once I grip down on it, then I should be able to pull off like this. And voila, I was able to pull off the jacket and leave just the bare wire on the inside like that. So that's what a wire stripper is primarily used for. Although you also have this cutting ability in the bottom of the jaw here that you can use if you need to cut off what I just did, that I can just snap it off like that and start again. So get yourself a good pair of wire strippers. The next thing we need to talk about are connectors. How in the world are we going to connect all these wires together? You could just take the two ends and, twist them together and put some tape on there, but I do not recommend it. Your wire organization is going to get really, really difficult, and it's also, you're running a risk of these things coming disconnected, and then that's going to be a pain to try to figure out what happened. So a couple of different types of connectors that we recommend would be either wire nuts or wire clips. These are the main two. So let's take a look at wire nuts. So with wire nuts, you actually would twist two bare wires together like this and get something that looks like this. And they run in different sizes depending on what size gauge wire you need. But basically, if you get a multi-pack that looks something like this, this says it's for 14 through 20. And it's a multi-pack of orange and blue ones, also got from Home Depot. You pick one, and then after you've sort of twisted your two wires together, you're going to take this cap, put it on there, righty-tighty, lefty-loosey, and you're going to keep tightening to the right until you really get it down there. And now the beauty of this is that that wire is not going to come apart unless you really try to force it apart. It's not going to fall apart on its own. And that's a nice way to make sure you don't have any bare wire sticking out anywhere. It's all covered and it's all connected really well. So that's how you'd use a wire nut. Our favorite is the wire clip. And the reason we like wire clips is because they come in lots of different variations that allow you to organize your wires in a much better way. Now, one of the ones that we really like are these, what we call inline or straight wire clips that look something like this. There are lots of different ones you can find. We'll include a link in the description to some of the ones that we like to use on Amazon. But essentially, they have these levers that you push up to release the socket like this. So now this is open on both sides. And now I can take a wire and I can place a wire that's been stripped like this and showing the bare wire and put it inside of this open hole here. And when I close down the lever, it has a nice snap to it. Then the wire's in there and it's not going to pull out. And then also if I put it far enough in there, then you also will not see any of the bare wire sticking out. And then on the other side, whatever we want to connect it to, we would do the same thing. We would just take the bare wire, stick it in there, snap it down, And now we have a good connection using a wire clip. Now let's take a minute and talk about wires. I know earlier we talked about wire gauge, but let's take a little bit of a more holistic look at wires and how to select the right ones, and some of the terminology that goes along with it. So inside of a wire, there are actually conductors. And conductors are things that conduct electricity and allow the flow of electricity to happen that will be detected by, like, the continuity meter we were talking about earlier. It's metal, right? So there's metal inside of a wire, and the metal part is what you would consider the conductor. You have this jacket on the outside which does not conduct electricity. That would be like the insulation. Now, depending on the type of wire you buy, it could have multiple conductors inside of one wire. The common types would be either one conductor, 2, 4, or 8, but you can find all different types in between as well. So in this particular wire, this is what is called a 16-2 wire, 16 gauge, 2 conductors. So I'll take my wire strippers and I'm going to use the back jaw part, the cutters, to just very slightly score the outside of this jacket by rotating it around. And then I'll use this motion to break it off, almost like a banana peel. And then this white insulation comes off, and inside I see 3 parts. I see this thread here, which is used to, in case you want to strip down the white jacket even further, you can pull it down and expose quickly a lot more of the inside. And then we can just sort of cut this off of here, the white jacket. I'll also, when I'm doing wire organization, be sure to trim this thread out. Don't let it hang around, it's really annoying. Okay, so now inside we have these 2 wires. So these are our 2 conductors, but they also still each have their own insulation around them. So in order to connect something to these wires, we're gonna get rid of that insulation as well, right on the end. So when you're stripping a wire, it's good to take, probably I would say 1/2 inch to 3/4 of an inch of length to create bare. If you go much longer than that, you're gonna end up with a whole lot of bare wire that's sticking out of your wire connectors, whether wire nuts or wire clips. So I'll just take this and we'll go about 3/4 of an inch, squeeze down, pull off like this. And now we have 2 wires that we can use to hook up to a device or to a power supply here. Another thing we need to know about wire is whether or not it's solid or stranded conductors. So this, as you can see, is stranded because the metal is in a bunch of different fibers that are twisted around each other on the inside of this insulation. Solid would mean that there's one single piece of metal on the inside. Now, either one is fine. They're good for different applications. We typically use stranded wire like this. Although I think typically you would use stranded for 20 gauge or thicker. And you probably, if you get to a smaller gauge wire, like a 24 gauge wire or 26, which is inside of like a Cat 6 or a network cable, those are probably not going to be stranded because the wire is already so small, there's not really room for a bunch of strands. So like inside of a network cable, you're going to see those are just one single conductor or solid. Now, wire gauge, which we mentioned earlier, is measured in AWG, or American Wire Gauge. All of the numbers we've been talking about so far, like 10, 14, 16 gauge wire, is a measurement of American Wire Gauge. Now, another thing you need to consider is whether or not your wire is shielded. Now, shielded would be if your wire, just inside the insulation layer, there was another layer of metal, like aluminum foil almost, wrapped around your conductors. And that would be there to keep electromagnetic interference from interacting with this wire when it's not supposed to. Typically, we do not use shielded wire unless it's for specific applications where it's needed. Now, another concept that's really important to understand as you're getting into escape room tech is the difference between power and signal. Now, for starters, a wire all by itself is neither power nor signal. It's what we do with it that determines whether or not it is associated with power and a power supply, or signal and a device that's giving some sort of output information. So if I have a piece of wire and I've connected it to an arcade button here that has a micro switch on the bottom, this micro switch looks something like this, and it has this little black tab that I can click like this. When I press this down, on the inside of this plastic housing, there are metal contacts that are touching together. And literally what it's doing is it's taking the red wire that I have connected into the prong on the switch, and it's internally creating a connection between the red wire and my black wire. So then I would get continuity, or a signal, across these. Let's take a look and measure with our multimeter to confirm this. So here, if I connect the multimeter to my black wire and my red wire. And I set the multimeter to a continuity test. Now if we click this switch, this is what we would consider signal, because I have the ability to conduct a signal across it by touching the two together with a switch or something else like it, but it is not transmitting power. So if I were to take this and switch it to volts to measure voltage, the number of volts that I'm getting is basically zero. I'm getting point something millivolts, which is basically nothing. So this wire, as I'm using it here, would be a signal wire. Now let's contrast that with using another wire that I hook up directly to a power supply on both the positive and negative side of power. So I have this wire now hooked up to my power supply using this wire connector going down to my power supply here. If I were to now hook it up to the multimeter while it's on volts, and let's get a reading here, I'm getting about 12 volts again here. So I am getting a voltage reading on this, which means this wire I would consider a power wire. So the reason this concept of power and signal is really important in the escape room world is because almost every device, every prop needs power in order to do something, in order to operate. But the thing that it does when it's complete or a group finishes it is typically give some sort of output signal to tell the next layer or the next prop to do whatever it's supposed to do. So the very last thing we want to talk about in this tools and terminology video is switches and the different terms you need to be familiar with and how they work. So let's go to the board and take a look at it. So a switch like this one, an arcade button that's connected to a micro switch, has 3 different labels on it. And we're going to take a look at what those labels are, because the labels on a switch like this one are going to be exactly the same labels you run into on a device or a prop controller, like maybe a Fright Props controller. On the output side, they use the same terminology. So it's really important to understand how these outputs of a signal work. So on my micro switch, I have the button here that we depress down, and then we have 3 different prongs that come out of it, and they each are labeled. The bottom one here is labeled COM, which stands for common. The reason it's common is because it's a shared pathway that can connect to both of these other prongs. The bottom prong here is called NO, or normally open, and we'll get into what that means in a minute. The top one is NC, or normally closed. Now let me ask you a question. If we were to imagine the bird's eye view of a room, and this is the doorway, and we draw a door like this, is this door open or closed? Of course it's open. So this would be normally open. Now, opposite would be if it was like this, that would be closed, normally closed. The word normally, the way I think about this is if the device is not being acted upon at all in its normal or default state, what does it look like? So if this is normally open, this prong here, and this one is normally closed, and it's how they relate to the common prong, then here's what you can imagine is going on the inside. So on the inside, there is a connection from the common prong up to the normally closed prong. So in a normal state, default state, when nothing is being acted upon this switch, there is a connection between common and normally closed, similar to this. And then if we act upon it by pressing the button down on the switch, it's going to cause a mechanical action that moves this little lever from here down to here, to now that common will connect to normally open. This is really important to understand because if we're deciding how to put together a circuit, let's say something really simple like a light bulb and a power supply, but we want to use a switch to control when the light bulb comes on, and we only want the light bulb to come on when we press the switch. Let's take a look at what that would look like. So if we draw a light bulb over here, and our power supply with a positive and negative side. Of course, if we wanted to just illuminate the light bulb, we could put a wire directly between negative in the light bulb and positive in the light bulb and turn it on like this. And the light bulb would come on. But since we want to use a switch to interrupt the flow of electricity to the light bulb, we need to break one of those legs here. So I'm going to disconnect this wire here, And the way that you can think about this is common should usually connect to wherever the source of power is, so that you then have the option of directing it outward to the device through either normally closed or normally open. So we're going to take this wire here that's coming off the power supply and connect it to common on our switch. And then if we want the light bulb to stay on all the time, then we would connect it to normally closed like this, because on the inside of the switch there already exists a connection right now that connects common to normally closed. So then we would have an illuminated light bulb. But of course, what we actually want is for it to only come on when we press the button. So we'll do the opposite. So instead of going to normally closed, we're going to go to normally open. Aha, because you see here on the inside, there is no connection between normally open and common. So there's no pathway for the light bulb to get the positive side of power from our power supply until we press this button, which causes this little lever on the inside to switch from normally closed to normally open, completing the pathway and turning on our light bulb. So that concludes tools and terminology, the first part of the Escape Room Tech Bootcamp series. But in the next video, we're going to be diving into hands-on projects that are going to teach you tons of stuff, starting with the escape room classic of hooking up a maglock to a door with a keypad, all the way to how to reverse, forward, and backward a motor or a linear actuator using relays. Don't worry, you're going to learn hands-on each step of the way. Be sure to check out each video as they come out. And also be sure to check out PuzzleCon 2025 coming up in September, where we're going to have an Escape Room Tech Bootcamp workshop where you can be in the room with us and learn in an even more hands-on way than this. And for more content like this, like and subscribe.